Hello, today we want to present assignment 3. The title is Design of Feedback Controller for Switch Mode Power Supply. Okay, this is group member. Okay, this is content. There are 3 content. Content 1 is explain the operation and determine the transfer function of each block diagram in figure 1. Content 2, perform the hand calculation to determine the converter parameter. Content 3, use MATLAB Simulink to design a stable converter feedback controller. Okay, now for content 1, feedback controller of a buck converter. A buck converter feedback control system adjusts the duty cycle of the switching signal on a consistent basis in order to manage the output voltage. One kind of this DC to DC converter that reduces the input voltage to a lower output voltage is the buck converter. A controller, a voltage feedback sensor, and a path with modulation PWM generator are usually involved in the feedback loop. For PI controller, there are 2 points. First, the error signal is then fed into a proportional integral controller. The PI controller processes the error signal to generate a control signal that will adjust the duty cycle of the PWM signal. Okay, this is the transfer function of PI controller. Okay, for PWM, the PWM generator takes the control signal from the PI controller and generates a PWM signal. Second, the duty cycle of the PWM signal determines the amount of time the buck converter switch is on and off. Okay, this is the transfer function of PWM. And next, switch. The PWM signal control the power switch, usually a MOSFET in the buck converter. When the switch is on, energy is stored in the inductor, and when it's off, the energy stored is transferred to the output. And this is the transfer function of switch. And lastly, for filter and load, the output filter typically consists of an inductor and a capacitor in parallel. This LC filter helps reduce the output voltage ripple and minimize high frequency components. The load in a buck converter system represents the electrical or electronic device that draw power from the converter output. Okay, and this is the transfer function of filter and load. And now move to content 2, calculation 1 and 2. Okay, start for calculation 2. DC output voltage 0 volt to 30 volt. This is from the equation. Input AC voltage 240 VRMS and 50 Hz. And then use switching frequency. We use 35K kilohertz. And max converter output current 5 ampere. Output voltage ripple factor we use 2.5%. And transformer ratio we use 4 and 1. Okay, from the transformer ratio formula, we can know the value of V2. Okay, and the value of V2 is 60 VRMS, and to find the V in, we have to times by square root 2, and then we get our V in is 84.853 volt. And now look at for D min. The equation is VO over V in. As we know, the VO in the equation is 0, and we will get the 0 value for D min. And for D max, we know the value of the value of VO is 32 volt, and we divide by 84.853, and our D is 0.3771. And now we calculate the value of R. The value of R is V out over IL. Okay, our V out is 32 and divided by IL is 5 ampere, and then we will get our R is 6.4 ohm. And next, we calculate the value of L min, which is the formula is 1 minus D times by R and divided by 2F. Okay, as we know, the value of D is 0.3771 and R is 6.4, and our value of F is 35K. And then we will get our value of L min is 0.057 millihenry. And for L max, the formula is 10 divided by L min. As we know, the L min we get 0.057 millihenry. We times by 10 and we get our L max is 0.57 millihenry. And next, we calculate the output voltage ripple, which is the formula is 1 minus D divided by 8 LCF squared and greater than 0.025. 0.025 is our output voltage ripple that we use is 2.5%. And we put all the calculate value, which is our D is 0.3771 and our L is 0.57 M and our F is 35K squared. And then we can get the value of our capacitor, which is C 0.112 microfarad. And then we calculate the value of IL max. As we know, the formula is IL plus delta IL divided by 2. And then the formula is phi plus 1 over 2 times VO divided by L and times 1 minus D times by T. Okay, we put all the value that we get and then we get our IL max, which is 5.4996 ampere. And then for IL min, which is 5 minus by 0.4996, and then we get our value of IL min, which is 4.5004 ampere. Okay, now we calculate the value of delta VO. Delta VO, the formula is R divided by VO, and R is our output voltage ripple. Our output voltage ripple we use is 0.025. So we times by 32, and we get the delta VO is 0.8 volt. And then we calculate our V out, which is D times by V in. As we know, our D is 0.3771 and we times by our V in is 84.853, and then we get our V output is 31.998 voltage. Okay, now we look at for calculation 1. Calculation for question 1, which is transfer function of buck converter. Okay, we set RC is equal to 0.6 that we assume that value. Okay, next is gain. The formula is V in divided by LC. As we know, our V in is 84.853 divided by L is inductor value and C is capacitor value. So we put the value that we get, and then we get our value gain is 1.329 times 10 power of 12. Okay, now next, our transfer function is 1.563 microsecond plus 1 divided by 1.094 S squared plus 63797.8 squared S plus 2.443 times by 10 power of 9. 0 is written at 60,000. At K1, we assume the value of K1 is 10,000. Okay, if we want to get the KP, the formula is KI divided by KP equals to the value 60,000. So we put the value of KI, which is 10,000, and then KP is equal to, we get the value of KP is equal to 0.16673. Okay, when phase making at 45 degree at 20 dB, the formula is 20 log 10,000 equals to 80 dB. And then 80 minus by 19.999 equals to 60.192 dB. 20 log Ki equals to 90.1. And then we will get our value of Ki, the new value of Ki, which is 1011.59. If we get the value of Ki, we also can get the value of Kp. By the formula is 1011.59, we will divide by Kp and equals to 60,000. And then we will get our value of Kp is 0. The new value of Kp is 0.0196. 0.0169. Excuse me. Okay, now my friends, we will present about MATLAB simulating for part 1 and part 2. Okay.
Okay, so I will explain about the MATLAB simulation. So we have two parts. One is about the block diagram for CCM power supply, and the second part is about buck converter with feedback controller. So this is the first part. So what we do here, actually why we're doing this is like in this PID controller block here, we put in the initial Ki and Kp gains value. As you can see, this is the initial. So we click apply, then we click OK. So the information will be stored here. And then also we need to alter the buck block also. We put V in inductor, capacitor, resistor value. And then we have to click run. Once we click run, it will show the output graph for the initial values of the PID controller, which is here, before Kp and Ki adjustment in PID controller. As you can see, this is the pole zero map. This is the board diagram. And here you can see is the output waveform. As you can see, the peak is very high. It goes up to 80. And this is not really stable. So after, I will skip the simulation because it takes so much time. So I already screenshot and put in the slide, so it'll be very easy for you. Next, for after, we change the values here also for the new Kp, Ki values as well. And then something like that. Then we click apply and we click OK. This one can stay because the V in inductor capacitor value is still remain the same. Then we click run, and what we will have is this. This is the pole zero map again, the board diagram again, and the V out, the output waveform. Now you can see that the peak is not as high as before. Before it was 80, now it is 60. So it is much more stable. Next, we go to the simulation part 2, which is feedback controller, buck converter with the feedback controller. So here we build the buck circuit over here. And what we have few scopes to show the outcome. And here we have the circuit. What we have to do is here. This is the DC voltage supply. We put in our V in value here. And then our diode is standard, as usual. RLC circuit, RLC branch here is type L, which is inductor. We put in the inductance value. Here we put in the resistance value and the capacitance value. And here we put the resistance value as well. Here we have the PID controller, just like before. And once we click run, the software will run and the circuit is simulated. And then we can check every scope for the outcome. And I will skip this part because if the software will take some time to run. I will straight go to the results, which is here. So what we have here is carrier signal. We can see the carrier signal is sort of like a distorted waveform, but it's still uniform. Next, we have the gate signal, which is also known as duty ratio. This is how it looks like, as you can see. Next, we have the sawtooth waveform, which is the feedback signal. The term sawtooth is because of the shape of the signal, so we know it as a sawtooth waveform. This is just a derivative of the shape of the signal, but this is the feedback signal. Next, this is what we really observe, the inductor current, IL max, IL min. So maximum and minimum, this is the waveform, sorry. So maximum is right here. You can see I marked it with a ruler, number 1. Maximum is at this peak, and minimum is number 2, right here at the bottom. So this is what we use to compare our calculated results and simulated results to see how much is far from the simulation. And our average is maximum and minimum divided by 2. That's how we get the average inductor current. So this is the output voltage that we get. It's also the same thing. You have the maximum, you have the minimum, and you can also do the same procedure to find average output voltage, which is the same thing. So let's move on to discussion. Adjusting KP and KI gains in a PID controller impacts system performance. The gain selection is crucial for stability, responsiveness, and overshoot minimization. This basically means like making the output much more stable. Like as I mentioned earlier, previously the waveform is peak at 80, and then it improved after the PID adjustment, reducing the peak to 60. Next, simulation reveals the difference between MATLAB result and hand calculation. This is for part 2. The parameters include maximum inductor current, minimum inductor current, average inductor current, Vout, and Vout maximum and minimum. So as we can see right here, I've already calculated the Vout in simulation exceeded the calculated values by 15.562 voltage, and this is due to the ripple effect. Here is the table. You can see inductor current, average, maximum, minimum. This is the calculation, and this is the simulation. It is different, but not so far. Here also you can see, and calculation simulation. This is where I mentioned is different. It exceeds by 15.562 voltage. Okay. Next, my teammate will continue.
Okay, for conclusion, okay, in summary, MATLAB assess the CCM switch mode power supply design without error. Okay, we can understand in the switch mode power supply is achievable through data evaluation and comparison with manual calculation. The CCM switch mode power supply outputs 0 to 50 volt DC. However, due to voltage ripple, the simulated output suffers 32 volt and possibly due to design inaccuracies or instability. Okay, that's all for our presentation today, and we want to thank you everyone for your attention. Thank you.